Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to kind of pick up taking that ideal gas law that we've now officially derived and using it as a good case study for how we deal with mathematical descriptions in chemistry, specifically how we can treat both our variables and our equations. So the first thing we have to really understand is there is a tendency to call the um, the complete description of a chemical system as its state. So we can define the exact state of a system using something called a state function. So a state function is going to include any description that fully describes our chemical system. So we've seen several of these, and the big ones are things that are going to be the variables that define the system. So things like the moles of gas, the pressure of the gas, the volume of the container, and the temperature. But it actually includes even more because these are going to control what the system looks like. But there's all kinds of response variables that include things like the density of the system. Again, depends on moles and volume, the entropy and enthalpy and Gibbs free energy. And we're going to be talking about a lot of this as we go through the semester. So one of the useful things, and one of the reasons we love gases, is for gases, if I know three of my state variables, so three of these four variables, then I can theoretically calculate not just the fourth, but any of the other state functions. So I can calculate the density, the entropy, enthalpy, Gibbs, and any other function you can include. And makes them really powerful. So we often want to be able to define our state variables, so we can define any of the other state functions. However, in order to do this, we need to have an equation of state. So this is going to be some equation that defines a given state function. So for example, the ideal gas law can be written as a state function of a equation of state for pressure, because it defines the pressure of a system in terms of the other three state variables. You can also rearrange the ideal gas law so that it is an equation of state for moles, volume, or temperature. And that's really powerful. And so this is one of the reasons we love our equations of state, because if you can identify the state function we care about, so any of these 8 state functions, if you have the appropriate equation of state, you can accurately determine that value. But as we saw with the ideal gas law, this often involves making a series of approximations. And what approximation we want to make can really define on what equation of state we'll use. Some, like the ideal gas law, work well enough most of the time that I'm not going to want to use a more complicated equation of state. And this balance of what state functions we use is really going to be at the heart of a lot of what we're doing this semester, is identifying state functions we care about, and then what equations of state we can use, and what approximations we're willing to make. So whenever I'm trying to characterize any of these systems, we're often going to be looking at bulk systems. So these are going to be simple whole phases. And the easiest way to define the system, and again, the first variable to a certain extent we can define, is what phase my chemical system is in. So we're going to be mostly this semester looking at our 3 major phases. So these are going to be liquids, solids, and gases. So we, however, want to start with the simplest and easiest of these systems. And that's definitely going to be gases. So if you're interested in liquid and solid chemistry, please hold on. We'll get to there eventually. But we need to go ahead and start with very simple equations of state before we can go to more complicated ones. And that way, in that sense, we're going to start with gases. Because biggest thing here is they are the most dilute. Because again, they have very low concentrations. And as a result, they tend to have the least amount of noise. Because as we saw in the deriving the ideal gas law, the most complicated part of a phase is going to be the molecular interactions. Gases minimize this, making them very well behaved. And it is worth noting that because they're the most behaved, a lot of early chemical research did focus on the behavior of gases over liquids and solids. There was also another big benefit here. in that we can use the gas expansion to describe the propulsion of a cannonball, because a cannonball is literally just being propelled by an expanding gas that shoots the ball out the bore of a cannon. But also, if we're looking at a steam piston is defined by essentially injecting hot gas, steam, which then expands, and as it expands, it cools off, and then you can go ahead and compress it back, releasing the extra steam. So this expansion and compression of gases really powered the formation of steam engines. And it's worth noting, a lot of these steam engines still on this steam piston format really defines a lot of our modern energy infrastructure today. For example, if you go to a coal power plant or a gas power plant, they actually generate most of their energy through a simple steam piston. And again, these same principles still hold with things like the internal combustion engine. So again, there's still a lot of big interest in this expansion and compression of gases. And because these are relatively simple, that's where we're going to start. But also, importantly, because these were two important questions in the beginning of the 19th century, as physical chemistry was developing, these were the problems of interest because that's where the money was. People wanted to know how these steam engines worked, and they were always paid by the military to make better weapons. So as a result, that's where a lot of the focus was. And so that's where a lot of the equations really focus on developing. So especially because a cannon can also be treated as a piston, just single stroke, sending something out, we're going to see a lot of our descriptions of energy really be talking about this piston model. So my apologies, we're going to see a lot of pistons in the first month of class. So let's go back to this idea of the state of a substance. So right now, we're not going to quite get to reactions. We're going to first have to define just the substance on its own. And the condition or physical state of a substance is going to be defined by its properties. And so these state variables are going to be these physical properties we care about. And they're going to perfectly, if we know all of them, we can perfectly describe the physical state of a substance. So a gas is going to be described by the state variables we've seen so far. First of which we have volume. So this is literally the volume that a substance occupies. This is what is called a size extensive property. And my apologies, but I'm going to be using this vernacular a lot. So a size extensive property is simply a property that depends on the amount of sample. For example, if I'm looking at a gas, any property that depends on the size of container is going to be a size extensive property. So do I have, say, a small flask of gas or the entire atmosphere? Similarly, our next big state variable is the moles of substance. So this is also going to be a size extensive property. And in practice, we're often determining this from some other piece of information, like the mass of substance. And we can do this as long as we have the molecular weight of the gas of interest. Now, the problem with size extensive properties is if I care about the nature of the gas, I might not care about the actual size of the sample. I might want to know how molecular oxygen behaves, and I don't care whether I have a liter of it or an entire room filled of it. I want to know how the gas itself behaves. And in these cases, we often care about something called a size intensive property. So something like pressure is going to be size intensive. So the amount of pressure a substance exerts on its surroundings does not depend on the size of the sample. So for example, the atmosphere will apply 1 atm of pressure on its surroundings. And if it's at equilibrium with a balloon, that will also have 1 atmosphere of pressure. Doesn't really depend on the amount of sample I have. And then our last of our 4 state variables is going to be temperature, which again is going to be size intensive. And as we know, this is going to be essentially a metric of how much energy is embedded in the system. So we have energy embedded in the system. the amount of force exerted on the surroundings, and then two properties that tell me about how much substance I have. Now, a very useful feature is so now I've got four state variables. And if I have four state variables, I only need three variables to define the system. Similarly, we can scale this up or down. If I'm looking at a system that has three state variables, I only need two state variables to perfectly define the system. If I have 10 state variables, I only need nine to define the system. Because the idea is that our equations of state should be able to determine that last variable from the other ones. So for example, using the ideal gas law, if I know three of these four variables, I can always determine the fourth. And this can apply for any sort of system. Now, the issue is that we only work well if we're dealing with one or two variables. We don't like to deal with four. So this often means we're going to try and find a way to fix some of these variables. And it turns out the easiest variable to fix is going to be the amount of substance, so the moles. And this one is actually relatively easy to fix because we can do this by defining our system. So for example, if I have an open system, these are going to be very problematic to handle because if I have an open system, substance can either enter or exit the system. And this allows for the amount of substance to change. So if I've got an open flask, the moles of gas in there can go up or down freely, which makes it kind of a nightmare to study. So instead, we're often going to opt for what's called a closed system. So a closed system is just putting a simple stopper in the flask. So that prevents matter from going in or out, and that fixes the number of particles or the number of moles of each atom inside the system. And that makes it a lot easier to study. So we tend to really like using closed systems. And so as a result, most of the time when we're going to be developing equations, we're almost always going to start by looking at closed systems. And then if we're being really ambitious, we'll try and modify those equations so that we can extend them to open systems. Now, if we go ahead and work with a closed system, we've now successfully defined um, the moles of substance and kept that fixed. But that still leaves us with three variables. So pressure, volume, and temperature. Now, three variables is where I can start to really kind of do something because that means we can graph it. So in this case, if we're keeping our moles constant, we can examine the remainder of these three variables using our favorite equation of state, the ideal gas law, and develop a relationship in between pressure, volume, and temperature. The problem is when we do this, we develop a three-dimensional surface. And it turns out three-dimensional surfaces, not necessarily the easiest thing to work with. So in practice, what we're often going to do is we've already fixed the moles, so we're often going to end up fixing a second variable. And depending on which variable we fix, we'll end up with different sets of equations. So for example, I can go ahead and fix the pressure. I can go ahead and keep the amount of pressure in a system constant. This can be relatively easy to do. Most systems have a constant pressure simply because they're exposed to the atmosphere. So if I have a balloon, it's under a constant 1 atmosphere of pressure. And when I do this, that leaves my only variables as volume and temperature. And these are going to have a direct relationship. And so if I keep pressure fixed, this is called isobaric conditions. And the equation that results from this is called an isobar. So in the isobar, you'll notice we derived an equation with a direct relationship of volume and temperature. Congratulations. This is Charles' law. Yay. Now we can repeat this for fixing the other three variables in turn. So if I fix volume, I have a direct relationship in between pressure and temperature. And when I do that, I end up uh, uh, an isobar is Boyle's law or Charles' law. If I fix volume, I end up with an isochore. So again, isochoric conditions, constant volume, and the equation is an isochore, and I end up with Boyle's law. Or sorry, Charles' law. Um, uh, or sorry, isochoric is Gay-Lussac's law. And then the final case is I can go ahead and keep temperature fixed. When I do this, it's isothermal conditions, and the equational form we get is going to be the isotherm. Now this one is fun because now we've generated a inverse relationship in between pressure and volume, and this is going to be Boyle's law. So again, in practice, it's going to be hard to deal with all three variables changing constantly. So instead, we'll fix one variable and we end up having a simple fixed condition reaction, which helps simplify this system a lot. And so again, this idea of fixing variables to get simpler equations is going to be something we're going to do a lot with our equations of state. So all of this so far, we've really been ignoring the identity of a system and looking at systems that are only one type of gas. However, we can try and extend all of these to develop a slightly more advanced equation of state, because it turns out I can go ahead and use the ideal gas law to determine the pressure exerted by each component of a gas on the container independently. So I can look at the pressure, and so if I'm looking at atmosphere, which is made of oxygen and nitrogen, I can look at the pressure a given amount of oxygen in a container exerts on the surroundings using the ideal gas law because it gets to ignore its neighbors. And then we can do the same thing for the nitrogen. So we can determine the amount of pressure exerted by the oxygen and the amount of pressure exerted by the nitrogen. Now, this gets me to what are called partial pressures. So this little italics P with the subscript stands for the partial pressure, the pressure exerted by a single component. Turns out we can use something called Dalton's law to determine the total pressure just by simply adding together these partial pressures. And if we then insert these component gas laws, that means that if I know the amount of each substance and the temperature and volume, I can go ahead and predict the total pressure, which makes sense because if I also know the amount of each substance, I can find the total moles and use the ideal gas law that way. Now, one of the nice features is we can then use this expression of partial pressure to go ahead and rewrite the system in terms of mole fraction. So if I include a moles total over moles total expression in here, so the same as multiplying by 1, we end up with a nice little first term here, because here we've got the moles of a single component over the total moles, which is just the definition of a mole fraction. But on the second term, we have the total moles times RT over volume, which, hey, that's just the ideal gas law for the total pressure. So this means that not only can I determine my partial pressures from the moles of each component, I can also determine it from the mole fractions of each component. Where again, just as a reminder, the mole fraction is simply just the moles of each component divided by the total moles. So this is actually fairly useful. And what this does is it really lets us express our mole fraction not only as a molar ratio of the amount of each substance over the total, but also of the partial pressure of each substance over the total pressure. Now, one of the reasons why this is really useful is because this means that I can now use partial pressure as a stand-in for a mole fraction or a way to describe the composition of a substance, which again is a really powerful tool. Because now we can go ahead and take that partial pressure, and as long as we know the pressure of the system, very often 1 atm, it turns out I can figure out the mole fraction. So for example, if I'm looking at atmospheric composition, so the atmosphere composed mostly oxygen and nitrogen, and it's about 21% or a mole fraction of 0.21 oxygen. So if the total pressure is 1 atm, good definition of the pressure of the atmosphere, then that means that just by inserting into this expression, I can determine the partial pressure of oxygen is about 0.21 atmospheres, and the partial pressure of nitrogen is about 0.79. Now, again, one of the nice parts is so far we're using the ideal gas law. And under these ideal cases, it means we can treat each of these gases independently. The partial pressure of oxygen doesn't really interfere with the partial pressure of nitrogen. And again, that's going to be really useful and very handy. Now, one of the things that we start running in here is that you'll notice it's going to become quite burdensome to constantly be dealing with the moles of substance in the volume. Because again, these size extensive properties aren't going to be terribly useful if I'm trying to look at the atmosphere. So instead, in when looking at gases, we often use a new different kind of fun state variable um, called the molar volume. So the molar volume is just going to be the volume of the gas over the moles of the gas. Now, the nice part here is that if I have two independent size extensive properties, volume and moles, any ratio of two size extensive properties gives me a size intensive property. So the molar volume, or the liters of gas occupied by liters of volume occupied by 1 mole of gas, doesn't depend on the amount of substance. Instead, what it really is a form of concentration. So if we take a look at this, you'll note that this is just going to be the inverse of molarity. So again, it can be used in a very similar way, with the major advantage of the molarity, or the molar volume, is going to be usually a typically more useful number. But also notice that the molar volume is also going to be a lot easier to calculate, as it only depends on the temperature and pressure. And these are going to be a lot easier to measure because, hey, if I have a thermometer and a barometer, congratulations, I now know the molar volume, or the concentration of the gas, which is really useful. However, if I'm looking at the molar volume, we often want to have a reference molar volume. So what would I expect the molar volume to be? There's two classic reference conditions for this. The most common of which is the standard temperature and pressure, which is defined at 1 atmosphere and 0 degrees C, because this is going to be relatively easy to measure. And this also gives us a good kind of benchmark, because under these conditions, 1 mole of gas occupies about 22.4 liters. So again, a decent set of volume. However, I tend to prefer a different standard reference point, which is the standard ambient temperature and pressure. So this is SATP. So this stands for 1 bar and 25 degrees C, or about 77 degrees Fahrenheit. I tend to refer to this one much more because, as we'll see when we get to chemical systems, this is defined as standard conditions. So when I often ask for standard temperature pressure, what I'm really actually talking about is standard ambient temperature and pressure. And at this point, notice that that extra 25 degrees C and that little bit of difference in pressure does make a difference, as this is about 10% higher than the standard temperature and pressure. But also, it does show just how much a gas can expand when you go from freezing to room temperature. So this brings us to the end of our description of ideal gases. So next time, we're going to talk about when the ideal gas law breaks down and how we can figure out that it's not working anymore. Until then, take care.